An ordinary differential equation, or ODE, involves a function of a single variable and its derivatives. The word ordinary distinguishes it from partial differential equations, which involve multiple variables. The order of an ODE is the highest derivative it contains. A first-order ODE involves only the first derivative. A second order involves the second derivative, and so on. The classic example is Newton's second law: force equals mass times acceleration. Since acceleration is the second derivative of position with respect to time, this is a second-order ODE. Solving an ODE means finding a function that satisfies the equation. The solution generally contains arbitrary constants, one per order, which are pinned down by initial or boundary conditions. ODEs govern pendulums, electrical circuits, chemical reactions, and population dynamics. A separable equation is the simplest class of ODE to solve and arguably the most elegant. It is a first-order equation that can be rewritten so that all terms involving the dependent variable appear on one side, and all terms involving the independent variable appear on the other. Once separated, both sides can be integrated independently, turning a differential equation into a straightforward calculation. The classic example is exponential growth. The rate of change of a population is proportional to the population itself. Separating variables and integrating gives the familiar exponential function. Radioactive decay, Newton's law of cooling, and compound interest all reduce to separable equation. The key insight is recognizing when a complicated-looking equation can be pulled apart into two independent integrals. A linear first-order ODE has the form, the derivative of y plus some function of x times y equals another function of x. The term linear refers to the fact that y and its derivative appear only to the first power no squared, no products of y with its derivative. This linearity is enormously useful because it guarantees a systematic solution method using an integrating factor, a cleverly chosen function that, when multiplied through the equation, transforms the left side into the derivative of a product. The method always works and always yields a closed-form solution. Linear first-order equations model mixing problems where a substance flows in and out of a tank at known rates. They also model simple electric circuits with resistors and capacitors. An exact equation is a first-order ODE that can be recognized as the total derivative of some potential function set equal to zero. The condition for exactness comes from the symmetry of second partial derivatives, a test that immediately tells you whether the equation is exact. When it is, finding the solution amounts to reconstructing the potential function through integration. When it is not exactly exact, an integrating factor can sometimes be found that makes it so. Exact equations arise naturally in thermodynamics and conservative mechanical systems, where physical laws can be expressed as potential functions. They represent a deep connection between differential equations and the geometry of surfaces. The Bernoulli equation, named after Jacob Bernoulli, who studied it in 1695, is a nonlinear first-order ODE that contains y raised to some power n. Nonlinear equations are generally much harder to solve, but Bernoulli discovered a substitution that transforms this particular form into a linear equation. Replace y raised to the power 1 minus n with a new variable, and the nonlinear equation becomes linear solvable by the standard integrating factor method. This trick is one of the earliest examples of a substitution that tames a nonlinear equation by reducing it to a known linear form. Bernoulli equations appear in fluid dynamics, population models with crowding effects, and models of two-more growth. When the order goes beyond one, linear ODEs split into two parts, a homogeneous solution and a particular solution. The homogeneous equation sets the right-hand side to zero and captures the natural behavior of the system, its resonant frequencies, its decay rates, its intrinsic oscillation. Solutions to the homogeneous equation form a vector space. Any linear combination of solutions is itself a solution. The particular solution then accounts for any external forcing. For equations with constant coefficients, the homogeneous solution is found by assuming exponential solutions and solving a characteristic polynomial. The result governs vibrating springs, RL, C electrical circuits, and the oscillations of bridges. The Tacoma Narrows Bridge collapse in 1940 is often cited as a catastrophic example of a driven second-order system reaching resonance. Often, a single equation is not enough. A system of differential equations describes multiple interacting quantities simultaneously, each evolving in time, each affecting the others. The predator-prey model is a famous example. The rate of change of the rabbit population depends on both the number of rabbits and the number of foxes, and vice versa. Systems of ODEs can be written in matrix form, and their behavior is governed by the eigenvalues of that matrix. Real eigenvalues produce exponential growth or decay. Complex eigenvalues produce spiraling, oscillatory behavior. A zero real part produces neutral cycles. The geometric picture of solutions in phase space, called a phase portrait, reveals the qualitative nature of the system at a glance, without solving it explicitly. When a function depends on on more than one variable, say both position and time, ordinary derivatives are no longer sufficient. Partial differential equations, or PDEs, involve partial derivatives with respect to several independent variables. They are dramatically harder than ODEs, so hard that most PDEs arising in physics have no closed-form solution and must be solved numerically. The three canonical types, elliptic, parabolic, and hyperbolic, describe three fundamentally different physical phenomena, and each requires different mathematical tools. The classification depends on the signs of the coefficients of the highest order term, and it determines whether the PDE describes equilibrium states, diffusion, or wave propagation. Elliptic PDEs describe steady-state phenomena systems that have settled into equilibrium. The most famous is Laplace's equation. The sum of the second partial derivatives of a function equals 0. Solutions to Laplace's equation are called harmonic functions, and they satisfy a remarkable property. The value at any point equals the average of the values on any surrounding sphere. Laplace's equation governs electrostatic potential in empty space, steady-state temperature distributions, and the behavior of gravitational fields. Its close relative, Poisson's equation, adds a source term and describes the same fields in the presence of charges or masses. Elliptic PDEs have no preferred direction information propagates in all directions equally, and solutions are globally smooth. Parabolic PDEs describe diffusion, the spreading and smoothing of quantities over time. The heat equation is the archetype. The rate of change of temperature at a point equals a constant times the spatial curvature of the temperature field. Heat flows from hot regions to cold ones, and over time, temperature differences are ironed out. Joseph Fourier introduced his famous series in 1822 precisely to solve the heat equation. Parabolic PDEs have a built-in arrow of time. They are irreversible. Information from the past determines the future, but not vice versa. Beyond heat, parabolic equations govern diffusion of chemicals, the spread of pollutants, and the Black-Scholes equation of financial mathematics, which describes how option prices evolve over time. Hyperbolic PDEs describe wave propagation, phenomena where disturbances travel at finite speed without smoothing out. The wave equation is the canonical form. The second-time derivative of a displacement equals the wave speed squared times the spatial Laplacian. Solutions are waves. They travel, reflect, interfere, and carry energy across a medium. Unlike parabolic equations, hyperbolic ones preserve sharp features. A sharp initial disturbance remains sharp as it travels. This is why sound, light, and seismic waves all behave as they do. They transmit information at a characteristic speed without dissipation. D'Alembert solved the one-dimensional wave equation in 1747, writing the general solution as the sum of a right-traveling and a left-traveling wave, one of the most beautiful results in mathematical physics. Stochastic differential equation model systems driven by randomness. They extend ordinary differential equations by adding a noise term, typically a Wiener process, which is mathematical Brownian motion. The resulting equations require an entirely new calculus developed by Japanese mathematician Kiyoshi in the 1940s. In it calculus, even the chain rule gains an extra correction term because random fluctuations accumulate in a way that ordinary calculus cannot handle. SDEs are the foundation of quantitative finance. The Black-Scholes model for option pricing is an SDE. They also describe the motion of particles in fluids, the evolution of gene frequencies, and noise in electronic circuits. Solving an SDE means finding the probability distribution of outcome, not a single deterministic trajectory. Delay differential equations incorporate a time lag. The rate of change of a quantity depends not only on its current state, but on its state at some earlier time. This makes intuitive sense in many real systems. A thermostat reacts to a temperature measured moments ago. An immune system responds to an infection detected after a delay. A population's birth rate reflects conditions from a generation earlier. Despite their apparent simplicity, delay differential equations are infinite dimensional. Their solution space is far richer and more complex than that of ordinary ODEs. They can produce sustained oscillations and chaos that would be impossible without the delay. Delay equations are especially important in epidemiology, control theory, and the modeling of neural networks. Fractional differential equations extend the concept of a derivative to non-integer orders. Just as it is possible to take half an integral, the Riemann-Liouville and Caputo definitions allow derivatives of order 1/2, pi, or any real or complex number. This may sound like a mathematical abstraction, but it has deep physical significance. Fractional derivatives describe memory effects. In an ordinary derivative, the rate of change depends only on the current state. In a fractional derivative, it depends on the entire history of the function, weighted in a specific way. This makes fractional equations ideal for modeling viscoelastic materials that remember past stresses, anomalous diffusion in disordered media, and signal processing with long-range correlation. Fractional calculus was already being studied by Leibniz in 1695, yet its applications only began flourishing in the late 20th century.